Hello, friends. Welcome to the first episode of my astronomy series. I hope you guys are excited about astronomy. I don't know how you couldn't be, to be quite honest. Woo! Hopefully I can explain everything as simply as possible. If I can't and something still isn't really clicking with you, don't worry. It can 100% be with my teaching. So if you still would like further instructions on something, let me know and I can make an entire video on that. Okay, so astrophysics and slash astronomy definitely has an intimidating aura. Hopefully we can peel back the layers one by one and begin to see that, hey, maybe this isn't that scary. Yeah. So I went back and forth on where I wanted to start this journey, what made the most sense conceptually, and I settled on gravity. I think that's a pretty great spot to start. It's a fun spot to start. So let's begin. Through the centuries of effort, perseverance, and pure curiosity, which I love, legends like Newton and Galileo, which I'm sure you know of and heard of, pieced together a theory of gravity around the 1600s. So we're going to start right there. This series is going to assume that you have a decent understanding of algebraic concepts, but if you would still like more help, let me know and I can make an algebra course as well. So let's begin with Newton's law of gravitation. Wha-bam! Shwing! We are just going to start by writing out Newton's law of universal gravitation, and we'll talk about it, what it means, and we'll also do some examples. I'll do my best to keep this handwriting smooth, but understand I'm using a mouse. That's just an excuse. Even if it was handwritten, it would be horrible. Okay. F equals G M1 M2 over R squared. Woo! And this right here is Newton's law of universal gravitation, where the force of gravity equals the gravitational constant multiplied by the product of the mass 1, which is the first body's mass, times the second body's mass, m2, divided by the distance squared between them. So that means if there is let's just call this body is going to be m1, and then there's going to be another body over here, which is m2. This is r. The distance r is measured from the center of mass of one of the bodies to the center of mass of the other body. We're going to assume perfect spherical conditions for all examples from this point forward, just for simplicity reasons. So that's r, and that is what this r is, and we just square it. Let's just start out by calculating what the gravitational force between the sun and the earth are. So we are going to write F equals G, and we're going to substitute in variables one at a time just to help explain things as clearly as possible. So we're just going to leave G as G for right now. Mass 1 is going to be the mass of the earth. So M1 is equal to the mass of the earth, right? Because these are literally the exact same thing. I just don't want to use M1. I want to say M Earth for clarity reasons. So the mass of the Earth is equal to 5.97 times 10 to the 24th in kilograms. I'm also going to begin writing this stuff instead of times 10 to the 24th. I will begin writing 5.97 e to the 24th kilograms. This e, whenever you see a capital E in between 5.97 and then the exponent, this is just saying exponent 24. So times 10. E is basically equal to times 10 raised to the exponent. And this 24 is what is the exponent of the 10th. So that's mass 1, mass E, right? And then we're going to do mass 2 is equal to the mass of the sun. And the way we're going to draw the sun is a little circle with a dot in it. That's how we're going to represent the sun from now on. We're not going to do M and then S like we did with Earth, which is ME. We're just going to do mass of the sun, which is equal to 1.99 times 10 to the 30th kilograms. And written the preferred way, my preferred way, is 1.99. Since it's times 10 to the 30th, right? It's capital E to the 30th. The E is just in place of times 10. I just prefer writing stuff that way. I don't know.
That's my opinion!
So what we will have is the force of gravity is equal to the gravitational constant, which we'll fill out in a second, multiplied by, we need a long, nice line, multiplied by 5.97 times 10 to the 24th kilograms. And then multiplied by, so that's M1, mass of the Earth, multiplied that by 1.99 times 10 to the 30 kilograms, which is M2, the mass of the sun, divided by r squared, which we know, again, r is the distance between this center of mass of M1, which is the mass of the Earth, which means M1 is the Earth, to the center of mass of M2, which is the sun. And we know that r, I'm just going to give you guys these. We'll talk about how we actually learned these values. Right now, I'm just giving you these values of the mass of the Earth and the mass of the sun. But we will go in future videos how astronomers actually learned, and we're actually going to calculate these ourselves, how we know the mass of the sun and the mass of the Earth, because that's vital to understanding astronomy as well. So anyways, r is just going to be, we're going to write that in red. Is that even red? Maybe that's more orange, where r is equal to 1.5 e to the 11th meters. Cool. So now let's plug in r. So then it's the mass 1 times mass 2 divided by r squared. And we know that r is 1.5 times 10 to the 11th meters. And we're going to square this. Okay. So now let's worry about this right here first. Let's whip out our calculators and do this math together. I'm going to give a link to Desmos in the description, which is the calculator I'm going to be using. If normally I'm using a TI-NX or a TI-Nspire CX, if you would like to use the same calculator I use. I don't think it's actually necessary. Normally when I'm actually doing problems or something, I'm writing these by hand rather than on the computer, which is, it's just nicer to have an actual calculator. But this is not necessary, which is why we're just going to be using Desmos, because it works perfectly for us. Let's bring that over here, because we're just going to calculate this we're going to calculate this part first. So let's open up our parentheses, and then we're going to type in 5.97 multiplied by 10, and then shift 6 or caret is going to give us our exponent. Shift 6 will raise 10 to something. We're going to write it to the 24th. And we're just going to click right arrow to get out, the right arrow key to get out of our exponent. So 5.97 times 10 raised to the 24th. That's our mass 1. That's the mass of the Earth in kilograms, multiplied by the mass of the sun, M2, 1.99 times 10, shift 6 again to get into that exponent, to the 30, and then right arrow to get out of the exponent. This is going to give us the product of our numerator, and then we want to divide that product by our denominator, which is going to be in parentheses, because we're going to have to square our denominator, don't forget. 1.5 times 10, shift 6 to get into that exponent, to the 11th, 1.5 times 10 to the 11th, which is the distance from the Earth's center of gravity to the sun's center of gravity. And again, we're assuming perfect spheres. So 1.5 times 10 to the 11th, and then right arrow again to get out of the exponent. And then we're going to raise this we're going to square this again. And it gives us our answer right here. We can click enter and whatever, but it gives us our answer of 5.28 times 10 to the 32nd. So now I'm going to drag this over to the side. Now our equation becomes the force of gravity is equal to the gravitational constant times, and then we're going to use pink for this new number, 5.28 times 10 to the 32nd. And what are the units on this? It's going to be kilograms times kilograms over meters. But these meters got squared because this is written out. This is actually 1.5 times 10 to the 11th times 1.5 times 10 to the 11th. And both of these have meters. So then it's meter times meter, which is meter squared. So our units become kilograms times kilograms. Kilograms squared is going to be on top. Kilograms squared over meters times meters, or meter squared. And those are our units currently. And now we are one step away from calculating the force of gravity from the sun and the earth. We just need to now multiply this number we got by the gravitational constant. And we're going to write the gravitational constant in yellow. So G, how about this? Let me trace this. Oh, that's horrible. Is equal to 6.67 times 10 to the negative 11th. And what are the units on this? Are meters cubed over kilograms seconds squared. So the gravitational constant is pretty self-explanatory. This number is unchanging. It is a number that was dictated by pure observations. This number does not change unless the units change. This is what is used, and we'll go very in detail in the future about how this number is actually calculated. But for right now, it is a constant. It is unchanging. We use it whenever we need to calculate the force of gravity with Newton's law of universal gravitation. So let's head back over to our calculator, and we're going to take our number that we just calculated and multiply it by the gravitational constant. So we're going to open up our parentheses and do 6.67 times 10 raised to the negative 11th, and then multiply this by 5.28 times 10 raised to the 32nd. And that will give us 3.52 times 10 to the 22nd. So I'm going to bring over here, force is equal to, let's go with a nice like pink, 3.52 times 10 to the 22nd. But what are the units on this? Because we have meters cubed over kilograms times seconds squared multiplied by kilograms squared over meters squared. So if we're going to extract the units away just so we can do a simple calculation with those, which is meters cubed over kilograms times seconds squared. Multiply this by kilograms squared over meters squared. And this will give us the final units of, so if it's meters cubed over meters squared, we're going to be left with 1 meter in our numerator, so meter, and then times kilograms squared over kilogram. We're going to be left with 1 kilogram in our numerator, so meters times kilograms, and then all that's left is seconds squared on the bottom. Force of gravity between the sun and the earth is equal to 3.52 times 10 to the 22nd meters times kilograms over seconds squared. And you may have noticed that these units, are pretty familiar, maybe not. It's fine if they're not, don't worry. Kilogram times meter over seconds squared, which is the exact same as this, is actually equal to 1 Newton. So 1 kilogram times mass over seconds squared is equal to 1 Newton. So the actual final answer, this is correct still, but we want to simplify these units, is going to be 3.52 times 10 to the 22nd newtons. Yes! Nice. Okay. Hopefully we took it slow. If I didn't go slow enough, please let me know. But hopefully that you understand what's going on here. This is more or less just algebra right now, because all we have to do, we were given all of these constants of the mass of the Earth, the mass of the Sun, the distance between them, and the gravitational constant. In the future, we're going to talk about how the gravitational constant is actually observed and how that value is actually understood. So now this gives us our final answer of 3.52 times 10 to the 22nd newtons, which is the gravitational force of the Sun on the Earth. Nice. Cool. Okay, I hope that was good. I hope that it gets you excited. We just calculated how much the Sun is pulling on the Earth with just math. Math is simply the tool that we use to help us understand all of this amazing phenomena. Don't be afraid of the math. I'm not great at math. Do not worry. I will try and make this as simple as possible. I'm pretty smooth brained, so if I can figure it out, you 1000% can figure it out. Trust. Nice. Cool. I want to keep these small, short, and very digestible. So we're going to stop right there. I hope that was cool. Let me know if it wasn't. Okay, cool. Okay, nice. Bye.